All right. So, hey everyone. Thanks so much for attending this session today, and I hope you're enjoying your time at DevToberfest so far. So, my name is Aman Chopra, and I'm an ML engineer here at SAP, working on many LLM post-training topics. And today, I'm going to specifically be talking about how you as a developer can leverage different agent protocols like MCP, A2A, ACP, and others that you might have heard of to build multi-agent systems deployed right on our cloud platform, SAP BTP. I'm sure you guys may have seen some other sessions focusing specifically on MCP. While each session is going to give you a different perspective of MCP, my session is designed to give you a holistic understanding of how these different protocols are going to work together rather than just focusing on one protocol like MCP. And I'm also going to walk you through some various pro code demos so that you can implement these protocols in your own applications. So this session is going to be broken up into three parts. First, I'm going to discuss the motivations of AI agents and how they take LLMs to the next level. Then I'm going to be diving into this model context protocol, also known as MCP. And then finally, I will conclude and demystify the A2A protocol, agent to agent, and I'll be giving live demos or pro code demos for both of these protocols so that you can build your own multi-agent systems. So with that said, let's dive into AI agents. So before we get into the protocols, I first want to define what an AI agent is. And as we see on this screen, an AI agent is a very ambiguous term. So IBM claims that an AI agent refers to a system or program that is capable of autonomously performing tasks on behalf of a user or another system by designing its workflow and utilizing available tools. Salesforce claims that AI agents are a type of AI system that can understand and respond to customer inquiries without human intervention. Here at SAP, we define AI agents as autonomous systems that can perform multi-step functions without explicit direction. OpenAI is very brief. They claim that agents are systems that independently accomplish tasks on your behalf. Now, Anthropic has a much more verbose and detailed description, but they really draw this distinction, as they mention, between workflows and agents in the last line. And they claim that workflows are systems where LLMs and tools are orchestrated through predefined code paths, while agents, on the other hand, are systems where LLMs dynamically direct their own processes and tool usage, maintaining control over how they accomplish tasks. So, something common in all of these definitions is that, first of all, AI agents, or this term agents, there is some kind of autonomy. And I think Anthropic here really does a good job in its definition, as it's clearly differentiating between workflows and agents. And this distinguishing factor is really important because nowadays you have people in companies that are referring to your traditional RPA solutions and automations as agents, but in reality, AI agents have some type of reasoning and reflection component to them, which allows them to dynamically, as Anthropic says, accomplish tasks without having a hard-coded or predefined path. So we're going to be kind of unfolding this difference and definition a little bit more when we talk about the architecture. But before that, now that we've seen some definitions of agents, you're probably just thinking this is some kind of a buzzword. And there's not even a standardized definition, right? Why is it so confusing? So I want to walk you guys through this example that will hopefully convince you why an LLM alone can't solve certain tasks or answer certain queries. But by building an agent, your LLM is pretty much on steroids. So I want to start off by asking a question, like what was my resting heart rate last night? So I'm going to be using this framework, this LLM framework called Ollama. And Ollama really just allows you to run quantized versions of LLMs through your CPU on your local machine. And specifically, I'm going to be using this LLM called Falcon 2, which was released last year in 2024 by this institution called the Technology Innovation Infrastructure, and this is in Abu Dhabi. And this model is trained on 5 trillion tokens. It has 11 billion parameters and is quantized with Ollama using 4 bits. So let's ask this question. What was my resting heart rate last night? or on average last night. And let's see what the response is. So your resting heart rate last night was 65 beats per minute. So hopefully it's not too hard to convince you that this is a clear hallucination, right? We have no insight into how the LLM is even generating this response. So here we really need a way to connect the LLM to an external data source or tool which contains my heart rate data from last night. And that's really where agents are going to come in. So this brings me to defining the architecture of an AI agent. And understanding this architecture is really going to help you see why agents make a lot of sense for queries that we just saw, like computing my average heart rate from last night, which requires some external tool or data source. So as we can see in this visualization, agents have a few properties. First, they have this brain, which includes memory, and this is going to be the LLM in the case of an agent. They also have a set of tools, and these tools can be tools to search the web, an API to get weather, a RAG tool to retrieve information that you might want to feed into your prompt or into the context of your LLM call. And these actions are, and okay, the next component is going to be an environment. Um, and in this environment, the agent is going to be able to take actions, and these actions are the tool calls themselves. So now what this brain or this LLM is going to do, it's going to evaluate the observation that's retrieved from the tool call, and it's going to see if it needs to take another action by calling another tool to get more information, or if it answers the final or the user query. And in that case, if the user query is answered, it's going to output that back to the user. And this is really going to be this feedback loop that's going to continue until a final answer is generated. So if we use this agent to answer a question about my average resting heart rate from last night, we would define a tool, first of all, to fetch my Apple Watch heart data, for example, heart rate data, or we could use a different provider like maybe Strava or Garmin. And we're also going to need a tool to perform arithmetic. So we're going to have two tools in total that the agent has access to. So in iteration number one, the LLM is going to take in this input query, which is asking, what is my average resting heart rate from last night? And it's going to decide, okay, I need to make a tool call to fetch heart rate data using perhaps my Apple Watch as a data source. And then the tool call is going to give back an observation to the LLM, which is going to be some list of numbers. Maybe it's 5 minute readings of what my heart rate was from last night. Now, in the next iteration, the LLM decides, okay, I haven't answered the user's query, so I need to, it's going to reason and decide that, okay, I need to use another tool, which is going to be this calculator tool. And this calculator tool is going to go and add up all of the numbers in the list and divide by the length of the list to compute the average heart rate. And then after this tool call in iteration number three, um, the LLM would have observed perhaps 54 beats per minute from the previous iteration. And finally, the LLM will reason and decide, okay, I've reached a final answer, 54 beats per minute, and it's going to return that back to the user. So one thing that I should mention and to keep in mind is that now today we have many powerful LLMs available that already have reasoning capabilities baked into them. So for example, OpenAI's O series like your O1, O3, O4, DeepSeek's R1, Anthropic Claude 3.7, Google Gemini 2.5, these are all your reasoning models which can generate chain of thought reasoning, which is going to allow the model to reason internally but still only relying on its internal knowledge rather than getting observations and context from external tools. So maybe this would allow us to ditch the calculator tool, for example, in the example that we just talked about, to compute the average of a list of numbers. And the LLM might be able to just perform this simple computation within its chain of thought. But in general, it's still useful to bring in external tools like a calculator tool to ensure that there are no hallucinations and to bring in external context like I've been reinforcing. And this is really going to help the LLM expand on its pre-training knowledge. So I hope now you're convinced why LLMs are really going to lower hallucinations and take LLMs, why agents are going to take LLMs to the next level. So actually, in case you're curious, the first agentic framework to be released was back in 2022, and it was called the React Agent Framework. And this is actually a part of the paper's abstract, which you can refer to if you go to this link. But in the abstract, they claim that we apply our approach named React to a diverse set of language and decision-making tasks and demonstrate its effectiveness over state-of-the-art baselines, as well as improved human interpretability and trustworthiness over methods without reasoning or acting components. Concretely, on question answering and fact verification, and these are two famous benchmarks, React overcomes issues of hallucination and error propagation prevalent in chain of thought reasoning by interacting with the simple Wikipedia API and generates human-like task-solving trajectories that are more interpretable than baselines without reasoning traces. So this is really reiterating that same statement I was saying earlier about how agents can reduce hallucinations without even needing a reasoning model as the LLM, just by bringing in tools and having access to these tools alone. So this framework really paved the way for a multitude of other agent building frameworks, and some of these include like LangChain, we have LangGraph, Crew AI, and then in parallel, we also saw a lot of advancements in the LLMs themselves. So the LLMs are just getting larger and larger. Now we're having LLMs that are like over 1 trillion parameters. And then we also have like these more complex reasoning models as well that take agents to the next level with the chain of thought. And then there are also a plethora of applications and enterprise platforms that have been developed in the last few years. Like we have Microsoft Copilot, we have ChatGPT, we have Midjourney. Here at SAP, we have our Joule Copilot, and the list really goes on and on. And now for the rest of the session, I'm going to be focusing on these protocols themselves that have also been emerging in recent years. And these protocols, there are many of them. We have MCP, A2A, which I'm going to talk about in more detail today, but we also have others like ACP, ANP, and so forth. All right, so let's move on to MCP. And I want to first define what a protocol is. Just like we talked about agents and really unraveling the definition of agents. Similarly, before we get into MCP, I want to go to Protocol 101 and just define what a protocol is. So protocol is simply an agreed set of rules, conventions, or message formats that define how entities, which could be programs, systems, or agents, interact, communicate, and coordinate. So a protocol is really just a set of rules. I think that's the main takeaway here. And if we look at some examples of protocols, we have dozens that exist across various domain areas like networking, security, distributed systems, and blockchains, and even society. So if we go to networking protocols, right, we have our HTTP and HTTPS protocols for web communication. We have TCP/IP for transferring your data packets, SFTP for file transfers, right? And then security and cryptographic protocols, we have TLS, SSH, we have OAuth protocols. In blockchains, we have like Byzantine fault tolerance. Um, and then in society, we have like these peace negotiation protocols. So let's say you're at the UN, there are some rules that define who's going to speak first, how do you set an agenda and the order of topics to be discussed, any other types of diplomacy rules. In the context of immunization, we also have scheduling protocols so that children and adults know when should you take a vaccine, what are the recommended standards around those. And then for the AI agents, we have protocols as well. And these protocols are really just rules for agents to communicate to each other with each other and agents to communicate with tools. So MCP is where you have agent-tool interaction, and it's a protocol for agents to communicate with tools. And then A2A, ACP, ANP, and these others are for inter-agent or agent-to-agent interaction. So something I want to highlight about these protocols is that they are really going to help with integration and reusability. So, for example, for these peace negotiation protocols, like who speaks first in a diplomacy meeting, this came to be after many meetings were conducted and the UN agreed that, okay, we need some kind of a standard to be developed to ensure consistency or a consistent policy. So, similarly with HTTP and HTTPS, These also came to be because dozens of developers are writing their own REST APIs, and there needed to be a way to consistently share information using the same messaging formats, right? Otherwise, there's just a lot of overhead for each client to structure a request in a way that the server understands, and also for the client to parse the server's responses. So the agent protocols work very similarly as well. They're designed to make it easier for developers who are integrating agents and tools into their applications. So another point that I want to highlight is that we often see multiple protocols being used in the same context, right? So with networking, we are going to be using HTTPS, TCP, and DNS protocols simultaneously, right? Since HTTPS is going to define how your messages being sent between a client and a server, and how are they structured, those message formats. TCP will actually define how to order these data packets and control the flow across a network. And then DNS is going to define like the mapping between a domain name, public domain name, and a server's IP address. So these protocols are all used simultaneously, right? So with AI agents, we're also going to be seeing many protocols used in conjunction simultaneously with each other. So most commonly, you're going to see MCP, as I mentioned, which will allow these agents to interact with tools, and A2A or ACP will enable agents to interact with each other. So these will both be kind of working simultaneously. All right, so now let's dive deeper into MCP. So MCP stands for Model Context Protocol, and it was designed by Anthropic in pretty recently, last year in November of 2024. And it really, as I mentioned many times, enables this communication between LLMs and tools, but it's going to be via this standardized interface. So if we go back to the example where we asked that Falcon 2 LLM, right, what was my resting heart rate last night? We already identified that we need a tool to connect to some type of data source, whether it's Apple Watch, Strava, Garmin. And for the sake of simplicity, let's assume that all of this data engineering and ETL work is done, and the data is already stored in some database like HANA or MySQL or GCP's BigQuery. Doesn't really matter what the database is, but each of these databases have different APIs, which means that you as a developer have to integrate this API into your LLM workflow, and you have to handle these topics like authentication to the API, parsing the API response, constructing a prompt template with this response. And there's a lot more overhead. So now what happens if you start off with all of your data, for example, stored in SAP's HANA database, and then you migrate, for example, to BigQuery, or you go the other way around. You start in BigQuery and you migrate to HANA. So now as a developer, you have to rebuild this integration with this new API, right? And there's a lot of overhead to switch out APIs because before MCP, there was really no standardization. So the analogy I'm trying to make here in this visual is that before MCP, you needed to design these custom connectors. Like you would have to design a USB 2.0 for one API, Type-C for another, micro USB for the third API. These are all different APIs structured in different formats and different request payloads and responses. But after MCP, connecting to these tools becomes a lot easier because you can just use a vendor's pre-built MCP server to interact with their MCP compatible API. And this MCP server is like your standardized USB-C port, right? Like all Macs have nowadays, right? Or all devices really have. So for you developers out there, another way to think about this is like you're building this kind of wrapper around a function that is going to simplify and standardize how you interact with the function. All right, so diving deeper into the architecture itself of MCP. So MCP is going to have this client server architecture, and it consists of a client, which is going to sit in this host application. Um, and this client is really going to serve as the coordinator or the orchestrator. Um, and then we also have a server, and the server is going to provide a standardized access to the tools themselves. So as for this host that we talked about, that the client sits inside, this host could really be any LLM-powered application. So Claude Desktop, Cursor, whatever it is. And this host is essentially your end user's entry point into this whole system. This host is also responsible to spin up client instances. So the client is really code that is tied to the host. And the host also handles your user authorization. It maintains context across all the clients, and it actually conducts calls to the LLM itself. Now, the client's role is going to be to establish one-to-one connections with the servers and ensure secure transport via the protocol. So keep in mind that the client, again, is this code that is inside the host, and it's spun up only if the host decides it needs to access information from a server. Now, the servers are what actually expose the underlying tools, resources, or prompts. And these are going to be different primitives that are really defined by the protocol. And these primitives could allow access to a local file system, a database, or the internet, or whatever other tool that you define. And then finally, we also have some transport mechanisms that are in place between the client and the server, which could be either STDIO or server-side events through HTTPS. So if you use STDIO, which really has the most community support right now, then the MCP client is really going to be spinned up, or it's going to be spun up on the fly by the MCP host. If you use, for example, SSE via HTTPS, then you can deploy the MCP server as a standalone web service, and you can specify the client to connect to the server through HTTPS. And in this case, the client isn't going to be spinning up any servers. So the server will already be spun up and it's standalone and kind of decoupled from the system. All right, so something else I want to point out, and this comes right from the standard MCP protocol website, is that in their docs, they state that the protocol was designed with these four principles in mind. So first, servers should be very easy to build. This means that servers should be lightweight and should focus on specific, well-defined capabilities. You shouldn't be building an MCP server that's going to allow your LLM to connect to both the database and performing arithmetic. So it shouldn't be one server to do multiple things or multiple actions. Instead, you should have separate servers. So maybe one standalone server that establishes a database connection and another that is for computation. So the second point, servers should be highly composable. This really extends on the first point. And this really kind of reiterates that we want to be using this modular design, right? So this is similar to how your code bases, for example, evolved from the monolithic design pattern to our current microservice architecture. Now, the third point is that servers should not be able to read the whole conversation nor see into the servers or into other servers. So servers should just really be decoupled again. They shouldn't have any visibility into other servers. These are all standalone servers. And then finally, the final design principle is that the protocol is built to be extensible. So this means that developers can build additional features on top as needed. All right, so all of this sounds great on paper, but let me show you how an MCP interaction and workflow is really going to work in action. So for this example, we're going to be using Cloud Desktop, and this is an MCP host. And Cloud Desktop is one of the MCP hosts, for example, that only supports the STDIO transport mechanism. So Cloud Desktop is like one of the most popular MCP hosts. But this has an MCP client built into the platform already. So if we don't connect this client to an MCP server and just use Cloud Desktop out of the box, we'll see that it's not going to be able to answer the same query that we asked earlier, like what is my average resting heart rate from last night? Right, so we'll give it a second to respond. And we see over here that the LLM is responding and it's saying that it needs access to some kind of a device, right, or a data source to answer this question. So on the bright side, this is much better than the Falcon 2 model, for example, that we were playing around with via Olama. And this answer isn't hallucinated at release, right? At least. And this makes sense because this is a more advanced reasoning model. And this has like a chain of thought and it's trained to use tools if it has access to tools, instead of just making up answers that it might not know the answer to, right? So this really helps reduce the hallucination problem by using like a reasoning model. But now really this LLM is still inept without tools, right? It just can't answer this question. And this again is highlighting the fact that we need to design some kind of an agent architecture that has an MCP server incorporated into it. All right. So before we actually go through how we're going to build this server, first of all, I want to show you all this dummy data that I generated. And we have one table called sleep recovery. And this really has information on some sleeping statistics, like how much sleep I get at night, the percentage of deep sleep, what is my resting heart rate, what is my heart rate variability. And then I also generated some dummy data on fitness activity through the day. So how many steps do I get? What is the amount of calories burned? And what is my heart rate? And this data, for simplicity, I've just dumped it into a SAP HANA database. So now here's the code really how the server looks like. It's actually quite simple. And this is really just going to be a wrapper around the HANA API, which is built using this framework called FastMCP. And this is all built using Python. So FastMCP is really going to provide a convenient way to build both the MCP servers and the client. So if we go through the code, we're going to see that we have four tools that are defined here, right? We have this tool called list schemas. We have a tool, list tables, and a tool for describing tables. And then finally, a tool to run some arbitrary SQL, right? So not a very complicated server if we just try to understand the logic over here. In this server, we're just defining tools, and these tools are going to allow the client or the host to access the database. So once we connect the server to Claude Desktop and add an additional note in the prompt that it can find my data in a database that it has access to, we're going to see a series of steps, right? So the prompt, what was my average resting heart rate last night? You can use my heart rate data stored in the database you have access to, right? And then we see these series of steps. The first tool call that Claude Desktop makes is this list schemas tool call. Now it's connected to the MCP server. So it's going to first call list schemas so it can see what schemas exist in the database, right? And then the next, it sees that, okay, I see a wellness schema. And this wellness schema, out of all the schemas, the wellness one probably seems like it will contain your heart rate data. So now it's going to use the list tables tool, which we define in the MCP server, to list all the tables for a particular schema. And after getting the response by the server, it sees that, okay, there are a couple tables, that sleep recovery table and fitness activity, but sleep recovery probably has your heart rate data from your sleep, right? That's what it's saying. And then finally, Cloud Desktop is going to describe this table so it understands the table schema and understands what are the types of columns that the table has, so it can construct a query that will actually execute. And then it creates a query and it is going to it's going to decide, okay, I want to run this query using the run SQL tool. Can I do this? Right? And this is the query we see. And it's going to send it to the server and get a response from the server. And now we see that your average resting heart rate from last night was 64 beats per minute. So now we see that there's no hallucination and Claude Desktop is not inept anymore. It has access to this database tool. Okay. So what's cool is that there are thousands of MCP servers out there that companies have already released, and we can see this list. And on this marketplace, which is called MCP Market, you can see some of the popular ones for GitHub, for Perplexity, Cloudflare, Chrome, right? AWS, there are tons. Airbnb, Firecrawl, right? So This is really the beauty of MCP. There's a lot of community support. It's kind of like why Python gained so much popularity, right? Python has hundreds and thousands of libraries out there, and the community support is incredible. So if we wanted to use one of these community servers, we can just plug these in to an MCP host like Claude Desktop within seconds. And we don't need to worry about building the server ourselves or interpreting the API responses and handling that communication. The client in the host application is going to do that for you. So now that brings me to the client, right? We haven't talked about this MCP client too much. So we did agree on that Claude Desktop is our MCP host, and it contains a client. And the host and the client are going to be responsible for connecting to the LLM. So Claude Desktop, for example, is obviously going to use the Claude LLMs, right? But what if we wanted to use another LLM? Or what if we wanted an entirely different type of UI, not Claude Desktop's UI? So this is where it would make sense to design a completely new MCP host and client. So the official MCP docs actually provide a list of MCP hosts that have clients baked into them. And on this list, we see Claude Desktop, among many other applications like ChatGPT, Postman, LM Studio, um, Gemini CLI, Langflow, right? We have tons of applications that have clients and support for MCP. Um, but as we also see at the top, many of these clients and hosts don't have support for some of the MCP primitives that we talked about, like prompts, tools, and resources. All of them have support for tooling. But if we want to use these other primitives like sampling, we didn't talk about sampling too much, but as we can see here, every host is kind of designed differently and it has different support for the protocol. So this is where, again, we build our own host and client. We can really customize everything. We can customize what primitives we're going to bake in, how we kind of adopt the protocol, how the UI looks. Is it a CLI? Is it a UI? There's a lot of control. So here I've built a custom host, which is really just going to be a CLI application. So I haven't thrown any front end or UI onto it. But this has an MCP client baked into it. And this is going to interact with the same exact MCP server that we connected to Cloud Desktop to access the database from my sleep data. So the difference here is we're not tied to the same UI as Cloud Desktop, and we're in full control of the MCP client. So this allows us actually to use any LLM. So here, instead of using like Claude's LLMs, I'm using OpenAI's GPT-5 model, and this is accessed through our BTP service called the Generative AI Hub here at SAP. So now if I go and I ask a question like, what was my average resting heart rate last night? You can use my heart rate data in the database you have access to. And similar to Claude Desktop, we see that the agent decides, okay, I need to list schemas, right? I need to first figure out what data I have access to. And these are all the schemas it sees. And it sees that, okay, the wellness schema probably makes the most sense. So what I'll do now is I'll list all the tables in the wellness schema. I'll identify to find your heart rate and sleep session tables. I will identify last night's main sleep session, and then I'll compute the average heart rate during that session. And then it asks, please confirm. So then in the next step, I say, that sounds like a good plan. By the way, all the records belong to me. And now we see that it lists all the tables in the wellness schema like it said it would do. And then it sees that, okay, there's a table called fitness activity and sleep recovery. But I think sleep recovery makes the most sense, right? So I'm going to identify your main sleep session last night from sleep recovery. And then I'll compute the average heart rate. So it keeps checking with us to make sure, okay, am I on the right path? And this is similar to what Claude Desktop is doing as well. And then I say, yes, that sounds good. Again, proceed. And sorry, it takes a second. And then now it describes the table and it gets the schema of the table, sees what columns the table has. It has uh, columns for timestamp, for steps, and in sleep recovery, it sees that the schema for sleep recovery has a different schema for date, for sleep hours, deep sleep percentage. So it gets the schemas for both the fitness activity and sleep recovery tables, and then it constructs this SQL statement, and it asks us again, do you want us to run this query? Um, and is it fair to say last night is the last record in the table? And I confirm that yes, that's fair to say. And then it gives us the answer. And it says your average resting heart rate last night was 71 beats per minute based on the most recent entry in wellness sleep recovery. And it even gives us the date. So very similar to Claude Desktop, right? But we have a lot more control here. Sure, the UI isn't as nice, but it's kind of a trade-off. You build your own MCP host and client, you have more overhead of building this thing out, but you get a lot more control. Okay. So again, just if you want to look at the client code, we are using fast MCP to build a client. And let's look at the code. We don't really have to get into it too much, but we see that it is using like the chat.completions.create endpoint through the generative AI hub. So here in the client itself, in this host application, we are actually controlling what LLM is used. And you can see that here. We're using GPT-5, right? And we are getting all our tool calls. We're managing the context, right? We are storing all of the context into a memory, which it would be stored over here in this messages array. Um, so, yep. And then here we're defining kind of the actual host, which is a CLI-based application, right? So we are defining what types of arguments we can pass in, command line arguments, and so forth. All right. So hopefully now you have a better understanding of these MCP hosts, these clients and servers, and really their value in AI applications. So this concludes the MCP section of the session, and now I'm going to be diving into the A2A protocol. And this stands for agents to agents, and this was developed by Google even more recently than MCP in just April of this year. So it's still quite a new protocol. And it's really been gaining a lot of attention. And if you go to the official website, you can actually see like dozens of partners that are adopting this protocol, right? From Accenture to Atlassian to BCG to KPMG, Salesforce, SAP, even us, right? So you're going to see some announcements at TechEd, but there's a lot of hype with A2A, and a lot of big companies are using the protocol. So what exactly is this protocol, and why do we need it if we have MCP? So to answer this, I want to first reiterate that MCP, as we've discussed, enables agents to interact with tools, right? And these tools can be browser, third-party API, local file system, or database like we used, right? So A2A, on the other hand, as I've probably said now a few times, it's going to allow agents to interact with other agents. So the difference is MCP is agent to tool interaction, while A2A is agent to agent interaction. And that's kind of what we see in this diagram as well. So if you're building a multi-agent system where your enterprise has built some agents in-house and you want this agent to interact with agents built by another organization like Salesforce, GitHub, Meta, SAP, us, right? A2A is going to allow you to seamlessly connect these agents together, despite the fact that your agent might have been built in a framework like LangGraph, while the other agents might have been built using Google's agent developer framework or Crew AI. So furthermore, each of these agents, whether yours or the third-party agent that you're integrating with, may leverage MCP to connect to third-party tools. So this is why you really don't need to choose between MCP or A2A. Instead, you're going to use both of them simultaneously. These are both complementary protocols, and that's what we see here, right? We can use A2A to have your in-house agent interact with third-party agents, um, across your organizational barrier, but each of these agents will also be interacting with either their own in-house MCP servers or some third-party servers. So there's a multitude of other protocols as well. Like we see that there's ACP by IBM, we have ANP by Cisco, we have AITP by the Near Foundation, we have Agora by the University of Oxford, ACONP by LangChain, Loca by CMU, right? The list goes on. I actually found this really interesting research paper that surveys all of these different protocols and compares them across what scenarios they're used for, like what transport and discovery techniques they use and how established they are. So for the purpose of time, I don't want to talk too much more about the other protocols, but I would suggest exploring the reference research paper over here in case you want more of a technical deep dive. For now, I'm just going to highlight that A2A is the most democratized for agent-to-agent communication, while MCP is most democratized for agent-to-tool communication, right? The other protocols have their pros and cons, but they just aren't developed enough. Okay, so let's dive more now into A2A's capabilities. And it actually has some similarities to MCP in the sense, for example, that it follows this client-server architecture, where there's going to be a client that sits in a host application and that serves as this coordinator or orchestrator, and a server that provides standardized access to the agents themselves. So again, just like MCP, the host could be something like Cloud Desktop or another application that is essentially the end user's entry point. Now, the host must have an A2A client implemented in it, as the host is going to communicate to the servers via the A2A protocol through this client. And in the case of MCP, the transport mechanism could have been STDIO or HTTPS, as we discussed, right? But with A2A, the difference is that the only transport mechanism supported is HTTPS with JSON RPC payload format, similar to MCP in that case, using JSON payloads. Yeah, so now the servers that the host communicates with via the client are really just black boxes to the client, right? So from the client's perspective, the internal workings, like what LLM or tools are used or how memory management is handled, are not exposed at all to your client or host application. So the A2A servers and the agents themselves, it doesn't matter if they're built in different frameworks, what LLMs are being used, similar to MCP, right? It doesn't matter how the MCP servers are built, what language they're built in, whether it's Python, Go, Rust, right? It really doesn't matter, or what framework they're using or what APIs they're using under the hood. So that's kind of the same, we have that same standardization of an interface in A2A, just like MCP. All right, so with A2A, there are five main communication elements. So the first element is called the agent card. And this is really a JSON document that the server exposes to show the client the agent's identity, what its purpose is, and what tools it has access to. So I'm going to show you guys a sample agent card in a bit. And this is kind of similar to like on Hugging Face, how you have model cards for LLMs or any kind of ML model that just exposes what is this model used for and what are its properties. The next communication element is called a task. And a task is going to be represented by an ID and a lifecycle. And this task is really just a unit of work that the server conducts. So the task that is scheduled by the server and its status is going to be relayed back to the client whenever the client asks for it. So for example, the server might decide, okay, it needs to conduct a task to call a third-party tool, right? Or maybe it needs to use an MCP server to make this tool call. And since this tool call can take time, if it's some kind of long-running process, the client can always pull the server using the task ID to see if the task is complete. So now the third element is going to be a message. And the message is really going to contain the content that the end user is relaying to the server via the client, or that the server is relaying to the end user via the client. The fourth component is a part, and the part really allows you to, or allows the server and the client to include files, text, or any other modalities in the messages themselves. And then finally, the last component is going to be an artifact, which is a tangible output that is going to be generated by the server or the agent. And these artifacts are not really messages. They're going to be more like files, documents, images, or structured data, perhaps generated by the tools that the agent has access to. So as you probably feel, like these elements are pretty abstract and don't make a lot of sense. So you actually need to write some code to really understand these different elements. So I'm going to dive a little bit into the source code, first of all, for the A2A Python SDK, because in the source code, we can actually see these communication elements being defined. So what's interesting actually is that when the A2A protocol was first defined by Google in its initial release, it was really simple and there was no SDK. It was just kind of the set of rules that was defined and you had to implement the protocol. There were some scripts that were released with like the classes that define the server, the clients, the agent cards. But you really had to copy these scripts and maintain the code yourself. So now to make the maintenance easier, Google has released A2A SDKs in many languages, including Python, Java, JavaScript, and many more. So in Python, for example, if you go to the official repository on GitHub, you can explore these classes, right? For agent card, for example, we have this class that's defined in the official SDK, right? And we can see how it's defined. We see the message communication element being defined here. And then we also see the artifact element defined here. Similarly, you would see the task and the part elements also defined. So in the source code, you can really see all of these elements and understand kind of what happens under the hood a little bit better. And you can go to this GitHub repo in case you're curious. All right, now to see, like, for example, the A2A server, which you're often going to import when you're building an A2A compatible agent. What's interesting is, again, if you go to the source code, these servers are just standard fast API or Starlet-based servers, right? There's nothing really new here in terms of the server. The A2A is really just kind of rules and standards. In terms of the code, it's nothing special or new, right? It's really just using a lot of pre-built stuff. Um, you can even run the server using like Flask in Python, right? You can use any kind of framework you want. This is just a server, so it's kind of framework agnostic, as we see here, right? You can build a server using Starlet or Fast API. All right, so now let's extend the MCP example I showed you guys earlier by building a multi-agent system from scratch that can serve as a fitness, wellness slash lifestyle coach. So here is where we'll really see the A2A and MCP protocols coming to life. So what I've done is I've designed this front end slash UI that is connected to the multi-agent system that we can interact with using a web browser. Right, so this is going to be our entry point, a web browser, and then we have this front end application. For those of you who have built UIs in Python, which is what I used, I just used a simple Gradio. I used a Gradio framework to build this. And next, I built a host agent, and the host agent is really going to serve as this orchestrator. So the host agent is going to run locally on the same server or system as the front end. So we don't really need an A2A client to connect the front end to the host client, or to the host agent, sorry. The client usually comes into play when we're going to connect agents to third-party or remote agents, as we'll see next. So in this wellness system that I've built, there is one remote agent that I've designed to use the Python framework LangGraph, and it uses LangGraph um, instead of like CrewAI or Google ADK. And this agent is going to be a data collection agent. So this agent is connecting to HANA database via the same custom-built MCP server that we designed earlier. So the MCP server is nothing new. The code is all the same as we talked about when we were discussing MCP. In this case, because we need our host agent to communicate with the remote agents, we will have an A2A client in the middle that will facilitate the communication. So in this diagram, we also see that there are two other remote agents, and I haven't really implemented any other agent other than this one data collection agent. But I still placed them on this slide just to give you another perspective on why A2A is so powerful. As you can see, if we have a system with three remote agents, it doesn't matter how the agents are built. The first one could be built using LangGraph. The second could be built using Google ADK. The third could be built using Crew AI. We could have another built using N8N or, for example, OpenAI's Agents SDK. It really doesn't matter what language or what framework we're using under the hood. As we talked about earlier, the A2A's server's implementation details are hidden from the clients. So sure, we might lose some visibility by using this protocol, but with that comes the ease of integration, as the protocol will standardize all the communication. Something else I just want to mention as a caveat, if you're building all of this stuff in-house, like if you have um, agents that you're building in-house, you don't need to connect to third-party systems, you really don't need this protocol. The protocol actually might add more overhead and it might kind of increase your latency. There's just more overhead to use a protocol. But the beauty of the protocol is that when you have these third-party integrations with remote tools and agents, then the protocol helps with standardization. You can kind of just switch on and off, plug in, take out different servers, uh, different agents, A2A servers and different MCP servers. So it's kind of like microservice architecture, right? Like I talked about, it's very modular. All right, so in this multi-agent system, I just want to show you guys the agent cards for the host agent and the data collection agent. So these agent cards, as I mentioned, are documents, and these are JSON documents. So I have the host agent, which I've deployed locally on port 8000, and its agent card can really just be accessed through this URL. So you can send a curl command, you can throw this in your web browser. Um, but this is actually the standard URL that's defined by the protocol. After the base URL, you append this well-known agent.json suffix to the URL. Um, And then we also have this data collection agent, which for now I've just deployed locally as well on port 8001, and we see the agent card over here as well. But in reality, this agent might be some third-party remote agent designed maybe by another company, and it's going to be deployed remotely. Lastly, the Gradio-based UI, which is the front end, is also deployed locally for this example on port 7860. And here we also see informations on the agent cards for the host agent, as well as the data collection agent. All right. So with that said, I want to show you guys how this system is going to work in action, right? So I can type in a request uh, similar to the request I was using in the past, but here we have a data collection agent that is going to get data using the MCP server from a HANA database. Our orchestrator agent is going to be the first agent that's hit. It's going to take these requests from the UI or the front end, and it's going to decide, okay, where should I route this request to? If we had 10 agents connected to the host agent, maybe we have a data collection agent, maybe we have a data visualization agent that could be connected to like a Python runtime, which could be an MCP server that might build like visualizations and plots, maybe time series of like how my heart rate has progressed. This orchestrator is going to decide based on this query, where do I send it to? In this case, we only have one real agent other than the orchestrator, which is the data collection agent. So in this case, the orchestrator is going to decide I need to throw this request to the data collection agent. And another component that I've added into the orchestrator is to use a separate MCP server to perform analysis. So we're going to get some analysis on this data. So the data collection agent is going to return like a list of all the data of my heart rate readings from maybe the last 10 days or the entire time interval of the database. And the orchestrator is going to do some analysis via an MCP server that can conduct analysis. So here, when we send this query, it'll take a second, but we will see a response generated. Let me skip through this. Okay, so here we have our response. Your heart rate last night was 71 beats per minute. If you meant a different night, tell me the date and I'll check. Um, and for most adults, now we get this analysis, right? We get analysis of all of the data that the data collection agent sent back to the orchestrator, and the orchestrator is performing all of this analysis. So pretty cool example, but yeah, this is really how A2A works with MCP. It's really powerful, honestly, especially when you have these third-party integrations in play. But all of this, as I said, might still be abstract, and really the only way to learn about it is really building this stuff from scratch, right? So there's a bunch of tutorials out there. I'm happy to send you guys some resources as well if you'd like. But yeah, there's YouTube videos, we have SAP blogs, there are tons of other blog posts. But yeah, you got to build this stuff from scratch. You have to code it up to really understand how the MCP server and agent works at a lower level. With that said, I'm going to conclude this presentation. I appreciate you guys attending and um, for your patience, and I hope you learned something new about MCP and A2A. And with that said, yep, I'm gonna close off the presentation. If you guys have any questions, please send them in the chat and I will answer them and send them back to you. All right. Thank you, everyone. Bye.